All right, what you just heard there, folks, was an example of the Doppler effect. So if you notice there, as the car approached the camera where we were sitting is considered the detector. The pitch was higher when the vehicle was moving towards you, then it dropped to a lower pitch as the vehicle moved away. The change in frequency of sound caused by the movement of either source, detector, or both is called the Doppler effect. The Doppler effect is also illustrated in this diagram here. The source, which I call S here, or the book calls S, that's what's making the sound, is moving to the right with a speed of Vs. So source velocity, or source speed. The waves that the source emits spread out in circles centered on the source at the time it produces a wave. As the source moves towards the sound detector, which will be this guy or this girl, observer A, more waves are crowded up into the space. So we're making waves, but if we're moving in one particular direction, those waves get bunched up. More waves are crowded up, and the wavelength, you can see here, the distance between crests becomes smaller and smaller. Because the speed of sound is not changed, more crests reach the ear per second, which means that the frequency of the detected sound increases. So this person will hear a higher frequency sound because higher frequency waves are reaching. When the source is moving away from a detector, such as this person, observer B, the wavelength is lengthened, so spread out because the source is moving to the right. Fewer crests reach the ear per second, so this person would detect a lower pitch or lower frequency sound because of the low frequency due to the higher wavelength. Doppler shift also occurs if the detector is moving and the source is stationary. So if the guy's moving towards here or if she's moving away, same effect because you have a bunching up of waves or spreading out of waves. Okay, and there is a way to calculate that. Over here, highlight this. So the frequency that the detector perceives is equal to whatever the frequency of the source is emitting multiplied by a ratio here. Now V is the speed of sound, or the velocity of the sound wave in air. So whatever the particular temperature is that day, like what we figured out earlier, how fast is the speed of sound that day. And then we have the velocity of the detector and the velocity of the source. So either one could be moving or both or none, and then it wouldn't change. So that's what we would in fact have there, folks. So in the Doppler effect, V is the speed of the sound wave, Vs is the sound source speed, sub D is the velocity of the observer who is detecting the sound. The subscript D is used instead of the letter O to observe, yes, so getting it confused with 0. Now, please highlight this. To use this equation, we have to set up our situation in a particular way. So define the coordinate system so that the positive direction is always from the source to the detector. So we're going to set it up always such that the source is moving to the right or to the left, but the detector is always on the right-hand side. So we would have to, if we were looking at her scenario, we'd have to flip it. So the detector is always going to be on the right, and the source is always going to be on the left, the source that's making the sound. And then the equation will work all the time. The sound waves will be approaching the detector from the source, so the velocity is always positive. Try drawing diagrams to confirm that term behaves as you predicted based on what you've learned about the Doppler effect. So again, we want to make sure that the system has positive direction is from source to detector. So the detector is on the right, source is on the left. Sound waves will be approaching the detector from the source, so it's a positive. At the bottom here, they manipulate the equations, but I think we'll just leave the equation like this because it works out fine if we do that. We don't necessarily have to combine like terms to make it look like that. A couple of other things. Notice that for the source moving towards the detector, which is a positive direction, which results in a smaller denominator compared to the stationary source, and for a detector moving toward the source, etc., etc. So we'll see, and hopefully, if we have them moving towards each other, we should get a higher frequency answer, of course, because the sound waves are getting bunched up. And if the source is moving away from the detector, we should get a lower frequency. So that's a little check you can do when you do these questions, just to make sure you're getting the right frequency. So here's an example here. I added a little bit more to it here. A guitar player sounds C makes a middle C 523 hertz while traveling in a convertible at 24.6 meters per second. The car is coming towards you. What is the frequency that you hear? Assume the air temperature is 20 degrees C. So sketch the situation. So again, I sketched it so that whoever is going to hear the sound, the detector is on the right, and the source, the thing that's making the sound, is on the left-hand side. Now, of course, this could be moving, this one's still. This could be still, this one could be moving. Okay, yes, make sure you have to set it up like this. So we have, make sure that the positive direction is from the source to the detector. We did that. We're told that the frequency of the source is 523 hertz. So the frequency that the detector will hear, that's what we're asked to find out. We're told that the source is moving at 24.6 meters per second. The velocity of the detector, he's not moving, he's standing still, so that's going to be 0. So we have this. Now you see in this part here, they determine it using that rearranged formula. If we just use the original formula, let's see how we do. So the frequency of the source, 523. Speed of sound in air that day, at 20 degrees C, if you look back a bit, we could either use that formula, or I think we have a chart. Yes, air, 20 degrees C, 343. So 343 is the speed of sound that day, so that's V and V, 343, 343. The detector is not moving. The source is not moving, is moving. Now, since it's moving to the right, that's positive velocity. Moving to the left would have been negative velocity. So we can take a look here. 343 minus 0 is this 343. 343 minus a positive 24.6. So yes, two negative and positive make a negative. So we get that. And look at that. The ratio will be larger than 1. So in fact, the frequency will increase. If this had been moving in the opposite way, it would have been a negative 24.6. Negative and a negative is a positive, so we would have been adding 24.6 to this and getting a number less than 1 here, which would have decreased the frequency. Okay, so just be sure to draw that the source is going towards the detector from left to right, and in terms of moving to the right, that's a positive movement. In terms of moving to the left, that's a negative movement. All right. The questions I would like you to do are 1 to 4 in the bottom of this page. Just simply call it the Doppler effect. And right off the bat, I can see that here we're going to have to change this diagram backwards because the source is on the right and the detector is on the left. So redraw this with it backwards. Have the source making it sound this way and having the detector, which is the car, moving to the left. All right, so draw a picture for each one of these and you should be set.